Deep in the heart of our solar system, there is evidence of the greatest massive asteroid bombardment ever to strike Earth. A mysterious event of cosmic proportions made millions of asteroids spiral out of their orbits and bombard our planet. No one knew why it happened. No one knows if it could ever happen again. The source of this mysterious cataclysm is 93 million miles from Earth in the main belt of asteroids that lies between the orbits of Mars and Jupiter. Over 90% of all known asteroids are here. Each is a rocky fragment left over from the birth of our solar system about 4.6 billion years ago. Some are wider than New York State. At some point, millions of them peeled off from the main belt and hurtled toward Earth. Today, scientists are on a quest to fully understand how this happened and find out if it could ever happen again. Around the world, astronomers are watching our skies for asteroids to better understand this ancient bombardment and warn of future cataclysms. Telescope observatories are our eyes on the universe. Early warning stations scouring the heavens for NEOs, near-Earth objects, asteroids, and comets, which pass within 5 million miles of Earth's orbit. Dr. Don Yeomans is one of a group of NASA scientists dedicated to being the first to spot the beginnings of another asteroid storm.
The near-Earth space is filled with objects that can impact the Earth. In fact, we get hit by many tons of material every day.
Luckily, most of these asteroids fall unnoticed, impacting in unpopulated parts of the world or the ocean. Others burn up as they enter our atmosphere, creating spectacular shooting stars. But in the clear and rarefied air above Tucson, Arizona, astronomers of the Catalina Sky Survey have found over 140 near-Earth asteroids in just the past 12 months alone.
The primary goal of the Near-Earth Object Program is threefold, is to find them early, and find them early.
Of the more than 4,500 recognized near-Earth objects, 850 are bigger than 3,000 feet across. But even smaller NEOs would have a devastating effect if they collided with Earth. One such NEO stands out. In 2004, scientists discovered an asteroid they named Apophis, flying through space at about 28,000 miles per hour. It's about 1,000 feet across and named after the Egyptian spirit of darkness and death. And it looks like it's heading straight toward Earth. About the size of 3 football fields, Apophis would completely destroy a major city if it hit us. But scientists don't know yet whether Apophis will hit us or just come close.
It's going to make a very close Earth approach in 2029, April 13th, which is a Friday the 13th, of course.
But Apophis is just one near-Earth object. What if multiple NEOs head our way, all at the same time? Many scientists think that these NEOs are the last remnants of the ancient bombardment. To understand what might trigger such a cataclysm again, scientists need to know more about what happened in the past. The first question is when? The answer to that was discovered by accident during one of man's greatest scientific endeavors. Until the moon landings of 1969 to 1972, scientists knew very little about the makeup of the moon's surface.
Tranquility Base here. The Eagle has landed. Roger, Tranquility. We copy you on the ground.
But by 1972, Apollo astronauts had sampled and brought back over 800 pounds of lunar rock to learn as much as they could about our extraterrestrial neighbor. Back on Earth, NASA divides the samples between scientists, some to search for signs of life, others for traces of water. Professor Jerry Wasserberg of the California Institute of Technology is given the task of finding out the age of the rocks collected from the moon's surface. Before Apollo, most scientists assumed the moon's surface, like the Earth's surface, had been repeatedly renewed by volcanic activity.
Nobody knew what to expect. You had all sorts of wild and interesting points of view. Gene Shoemaker and the people of the U.S. Geological Survey had thought that the moon rocks would be rather young.
To find the elusive age of the rocks, Wasserberg uses Lunatic 1, a mass spectrometer that identifies chemicals in rocks by measuring their molecular weight. Wasserberg vaporizes and ionizes the moon rock samples. Then he accelerates them through a magnetic field. The chemical makeup of each sample immediately becomes apparent. Part of this makeup includes minute amounts of radioactivity. Radioactivity decays over time, allowing scientists to calculate a sample's age. Geologists had thought that the surface of the moon was made up of relatively young volcanic rocks that erupted from lunar volcanoes. And they also believed the craters of the moon were the remnants of these extinct volcanoes. Wasserberg dates the moon as being 4.5 billion years old. Then he starts to notice a strange pattern. Rocks collected from the moon's surface repeatedly show the same age, 3.9 billion years old. Not only that, these surface samples are made up of melted rock containing unmelted particles, suggesting they've been subjected to repeated intense heat and pressure. Heat and pressure much higher than could ever occur in a volcano. This means that the rocks and craters of the moon can't be volcanic. Their chemical composition suggests that these rocks formed deep inside the moon and somehow found their way to the surface. For Wasserberg, there is only one thing that could have caused the craters: asteroid impacts.
Geologists ignored impact craters. They considered it a non-process. But this process of erosion from space taking place as the dominant form of altering the surface of a planet simply did not register.
It didn't register because scientists had never observed an asteroid strike and couldn't begin to understand that erosion from space could have created thousands of craters, some thousands of miles wide. Now, though, scientists studying the few surviving craters on Earth have confirmed that the kinetic energy stored in an asteroid depends on its size and speed. An asteroid traveling at 10 miles per second releases energy on impact equivalent to 50,000 megatons of TNT. But double that speed, and the energy is equivalent to 200,000 megatons of TNT, producing a crater roughly 50% larger. The bigger and faster the asteroid, the wider and deeper the crater. When an asteroid strikes, this kinetic energy is released within a few milliseconds, melting and destroying the asteroid and moving and ejecting the ground surface. But is the release of energy great enough to force underlying ancient rocks up to the surface. This is one of the most powerful guns in the world. .3 caliber and 36 feet long. It's fired by explosively compressing hydrogen to 1 million times the pressure of air, propelling projectiles nearly as fast as an asteroid. This tiny ball represents the impacting asteroid. The target is a circular pit of sand inside an 8-foot diameter reinforced steel vacuum chamber. The man with his finger on the trigger is Professor Pete Schultz, an astronomer who specializes in high-velocity impact cratering.
The key here is to have the projector go deep, bring material out, and put it on top.
Schultz has laid down a layer of light-colored sand to represent the oldest underlying strata. He then pours purple sand on top to represent the younger surface layers. If Schultz is right, the projectile should completely invert the layers. The light-colored sand should end up on top. The gun and the target chamber date from the 1960s, so the control room where the gun is fired has a familiar look to anyone who's ever watched an early James Bond movie. The crater is almost 50 times bigger than the diameter of the projectile that created it. So if an asteroid fragment the size of a Harley-Davidson hits the Earth, this experiment shows that it would make a crater the size of the Yankee Stadium baseball field. If this impact is scaled up to planetary proportions, it would explain the size and composition of the craters of the Moon.
As we look inside the crater, we can actually see that the material that was below has now been brought up and put onto the top.
This demonstration shows how an asteroid strike can bring the underlying rock layers of a planet like the Moon to the surface. It explains why the Apollo astronauts repeatedly brought back 3.9 billion-year-old rocks. Based on the age of these rocks, Wasserberg proposed a radical theory that nearly all of the 300,000 craters on the Moon were caused by an asteroid bombardment 3.9 billion years ago. Unfortunately, few in the scientific community believed him. By the 1970s, Professor Jerry Wasserberg has come up with a theory that 3.9 billion years ago, the Moon was bombarded by a huge asteroid storm.
We established essentially a clear lunar chronology, that the Moon made a crust full of radioactive elements right after it formed. This was a veneer on the outside of the Moon, and then it sat there pretty quietly for about 500 million years, and then very large projectiles came in, very, very large projectiles, and punched holes in the surface of 500 to 1,000 kilometers in diameter and just stirred up the whole surface of the Moon, and then it stopped.
His bombardment theory was very controversial in the scientific community. Virtually no one agreed with him.
This level of antagonism or hostility toward this stupid idea was enormous.
They couldn't believe the timescale and magnitude of his bombardment theory. That's because scientists only had a few well-preserved surviving impact craters to study here on Earth. David Kring is a planetary geoscientist, an expert in the geological history of the solar system, and an expert on the formation of Meteor Crater in Arizona.
When the asteroid hit, it created an explosion that excavated about 75 million metric tons of rock and deposited on the surrounding landscape.
But the impact that took place here was less than 1,000th of the size of just one of the asteroid impacts Wasserberg was proposing. Many geologists refused to believe that nearly all the craters on the moon were made by asteroids. The scale of the event felt too catastrophic. So they began to pick holes in Wasserberg's theory. They started with the lunar sampling methods.
All of the Apollo samples came from only 4% of the lunar surface, and so those ages could have been reflecting only 2 or 3 impact events as opposed to bombardment of the entire lunar surface.
The Apollo samples may have been taken from a small area, but more worryingly for scientists, there was no known way in astrophysics for asteroids to suddenly fall out of their orbits and bombard the moon.
We had no mechanism as to why, as one of my colleagues, George Wetherell, said, why are they stored out there for 500 million years and they don't fall in, and then suddenly they fall in? I didn't know.
So for several years, Wasserberg's lunar cataclysm theory gathered dust.
Because of this criticism, we needed a new way to test the lunar cataclysm hypothesis. To do that, we needed samples from a much larger portion of the lunar surface, ideally samples from all areas of the lunar surface.
But how were they going to get more samples of the moon when the Apollo missions had ended? Seemingly, there was no hope of ever proving Wasserberg's theory. Then in 1982, a team of geologists finally found a tiny but crucial piece of evidence. Lying in the snow in Antarctica, looking just like a crushed Oreo cookie. Naturally, Wasserberg was one of the first people to hear of the discovery.
I get a phone call from Brian Mason, and he said, Jerry said, I just saw a lunar meteorite. I said, you're full of malarkey, Brian. You're hallucinating, you're making it up. He said, no. He said, well, why don't you come over and take a look? So I grabbed a taxi and my briefcase and ran over to his office, and we looked at it. And he said, what do you think? I said, it looks like a lunar meteorite.
This was the discovery that Wasserberg had been waiting almost a decade for. Since 1982, over 40 more fragments of lunar rock have been discovered. And statistically, they must have come from all over the moon, not just the Apollo sampling sites. And it's not just scientists finding these fragments. Out there scouring the world for all kinds of space debris are groups of professional meteorite hunters. Bob Haig is the Indiana Jones of the meteorite collecting world. Based in Tucson, Arizona, Haig has spent the last 25 years traveling to over 50 countries hunting for meteorites.
The way I hunt for meteorites in the field is get a good metal detector, go to a site that you know there are meteorites found, and just go. Bring my shovel, hoping to find one of these. Look at this. That makes it all worth it. That's the treasure from space.
Haig has amassed the largest private collection of iron and stone meteorites in the world. Like all treasure, it needs to be looked after and well protected. Haig keeps his collection safely locked up in a high-security vault deep beneath his house. With over 200 exhibits, Haig's collection is worth millions to the hundreds of collectors around the world. That's because some contain complete, beautiful, and gemstone-quality crystals, like peridot. These crystals form inside the asteroid in the superheated high-pressure conditions created during the impact, and also by millions of years of asteroids colliding and crashing into each other. Finding a meteorite is just the beginning. Haig then spends hours slicing them with a diamond saw. Once polished, each one of these slices can be worth up to $200,000. He's right. It is treasure from space. Haig is the first private collector in the world to own the holy grail of meteorites, a piece of the moon. this 3.9 billion year old rock is worth almost $1 million.
This is a moon rock that I discovered. This is called the Calcalon Creek. It's not very big, but it is a piece of moon, and I'm the first private guy, I guess, to say, that actually discovered a moon rock. To find a piece of the moon has been a dream for me.
At the time of the discovery of the first lunar meteorite in 1982, scientists had no idea how important it would be in proving Wasserberg's planetary storm theory. They also had little idea how a piece of the moon could end up on Earth. At the Ames Vertical Gun Range, Pete Schultz is busy rigging an experiment to show how Wasserberg's asteroid storm could bring fragments of moon rock to Earth. We've already seen how a tiny projectile can make a huge crater in soft sand. But what happens when a projectile is fired into a solid rock target? Is the impact powerful enough to break off a piece of moon rock and send it into space? A sandstone slab, our replica moon surface, has been prepared and the gun loaded.
The whole goal here is to see if we can't capture the process in the act of formation as we're slamming something off the moon at extremely high speeds into outer space and perhaps delivering it to the Earth. Oh, is that cool? Kapow!
In ultra slow motion, you can see how the sandstone explosively fragments. These lumps of rock travel upward and outward at speeds in excess of 1 mile per second, fast enough to escape the gravity of the moon.
It worked out like a charm. Here's the 1/4-inch projectile, about 6 millimeters, slammed into this block, ripped out these pieces, and on the moon, some of these pieces could have been launched beyond the escape velocity of the moon and been delivered to the Earth.
The mechanism is now clear. The 40 or so lunar meteorites so far found on Earth must have been ejected by a series of cataclysmic asteroid strikes at some point in the past. But when? Geologists now suspected that the answer to that date lay locked inside the lunar meteorites. The race was on to find the last piece of dating evidence for the greatest massive asteroid bombardment ever to hit Earth. Scientists were finally on the threshold of proving that our moon was once bombarded by a cataclysmic asteroid storm. The key lay in dating the 40 lunar meteorites found on Earth. Lunar meteorites are fragments of moon rock flung here to Earth from all over the moon's surface by random impacts. If they turned out to be the same age as the Apollo moon rock samples, it would prove that 3.9 billion years ago, all of the moon was bombarded at the same time.
In 2000, we finally did have the critical number of samples, and it did look like we were able to confirm the lunar cataclysm hypothesis.
Well, when your theory or hypothesis is validated in any way, it's a great form of gratification, particularly when lots of people are shooting at you saying, this is absolutely nonsense. I love that.
Scientists finally have proof that a massive asteroid storm 3.9 billion years ago devastated our moon with thousands of planet-sized rocks. They know when it happened, so the hunt is now on to find out what triggered the greatest asteroid storm of all time. Their search has led them deep into the heart of our solar system, to the asteroid belt, the only place that contains rocks big enough to account for the scale of this ancient bombardment. Scientists have begun to re-examine this supposedly benign and stable accumulation of rocks. In doing so, they have come to a new understanding of a strange force called resonance that could be powerful enough to send so many massive lumps of rock hurtling on a collision course toward our planet. This knowledge may finally unlock the mystery of how and why the planetary storm happened and whether or not it could happen again. Everything in our universe has a resonance or resonant frequency. Resonance is the natural frequency of vibration determined by any given object's size and shape. As an object encounters vibrations, it hits a specific point at which the vibrations cause movement. Take an engineer's shaking table and two identical balls on metal stalks. The different lengths of these stalks create a distinct resonant frequency. By changing the speed of the table, one of the stalks reaches its resonant frequency and begins to wobble madly. Change the speed of the table again, and the roles are reversed. The other stalk now wobbles out of control. This wobbling is caused by the release of energy that occurs when either of the metal stalks reaches its resonant frequency. Understanding how resonance works on the vast scale and across the gigantic distances of the asteroid belt, however, involves doing some very complicated calculations. The person behind the math? Renu Malhotra, professor of solar system dynamics, based at the University of Arizona in Tucson.
We have to ask, how is it that the asteroids are transported from the main asteroid belt into the planetary space?
Professor Malhotra calculated that Jupiter, the biggest planet in our solar system, was somehow influencing the asteroids.
Jupiter's gravity acting in a resonant way in the asteroid belt, in certain parts of the asteroid belt, and kicking asteroids into these very elliptical orbits that end up crossing that of the planets.
Once one of these resonant orbits is reached, the gravitational force exerted on the asteroids by a giant planet like Jupiter has the power to change their course through space. Anyone who's ever pushed their child on a swing can get a sense of the basics of this tricky concept. If you give the child a push at the highest point of the backswing, the size of the forward swing will increase. A little added energy over many, many swings will ultimately result in the swing going so far forward that it travels upward and over the supporting bar. Imagine that on a planetary scale. Resonance is so powerful that over millions of years, it can cause thousands of planet-sized asteroids to leave their orbit and in some cases, come toward Earth.
Every time one of these asteroids comes around close to Jupiter, Jupiter tugs on it just a little bit. And it goes around again, and Jupiter tugs on it just a little bit more. And it can actually move out of its circular orbit between Mars and Jupiter and come into the inner solar system where it can become a near-Earth asteroid.
After about 500 million years of being affected by Jupiter's gravitational pull, millions of asteroids were on a highly elliptical orbit. The stage was now set for a planetary cataclysm. The asteroids were on a collision course with Earth. Earth, 3.9 billion years ago. A gigantic storm of thousands of asteroids, some thousands of miles across, has been forced into a collision course with our planet by an invisible force called resonance. But what was our Earth like back then? Was there any life there to be threatened by the imminent bombardment? Steve Moishus is a geologist and astrobiologist at the University of Colorado at Boulder. He's looking for the oldest rocks on Earth to see if he can find any geological evidence of the ancient bombardment and to discover if life existed on Earth 3.9 billion years ago.
Being a geologist and looking for old rocks is a lot like looking for the proverbial needle in the haystack.
Moisius has scoured the globe in his search for the oldest rocks on Earth.
What's important about this sample is that it contains within it the oldest mineral fragments of rocks that formed on the Earth, in the Earth's crust, before the late heavy bombardment.
In order to unlock the secret of their exact age and find evidence of the bombardment, Moisius subjects them to another pounding. He pulverizes them to powder. This is geology on a microscopic scale. Each tiny fragment could be vital in understanding how and when the rocks formed. He searches for zircons, tiny crystals of mineral that can be precisely dated. Zircons are found in minute quantities throughout the Earth, from the oldest volcanic rocks to the most ancient river and marine sediments.
Zircon is a mineral that once it forms, it's very, very difficult to destroy it under normal geological circumstances. What is particularly fascinating about this mineral is that when it forms, it incorporates radioactivity.
This inbuilt radioactivity is the key to unlocking the age of the rocks. The ratio between the decay of radioactive and the production of non-radioactive elements is like having an inbuilt chronometer that starts ticking when the mineral forms. Moisius burns minute holes into the tiny zircons. He then takes the pieces that burn off and accelerates them through a series of mass spectrometers. This gives Moisius a date of 3.9 billion years. Exactly the same as the Apollo samples that Wasserberg analyzed more than 30 years ago.
Our oldest echoes of the first 500 million years of Earth history are preserved in a few rare, most ancient zircon grains. It seems to be that grail that geologists have long sought.
As well as providing an exact date of the planetary storm, these ancient rocks contain another grail, evidence of what our Earth was like during the bombardment.
Locked within this rock is chemical information that provides us clues about the nature of the earliest biosphere.
This sample from Greenland contains carbon isotopes, the basis of all organic life on Earth. Carbon combines with oxygen to produce carbon dioxide, and with hydrogen to produce hydrocarbons. These isotopes are a biosignature for life, suggesting that there was air and liquid water present on Earth, and their presence here in the rocks further confirms that life could later flourish here on Earth. Our world would have had a dense atmosphere, oceans, and land masses. Far from being an alien environment, it would be a world we could recognize today.
It wasn't a Chicken Little world where the sky was continuously falling. It was long periods of calm, interrupted by short periods of extreme catastrophe.
More important than evidence of an atmosphere, these samples prove to Moisius that there was some form of life existing on Earth that survived the bombardment and lives with us still. They're called extremophiles, unique microscopic creatures who live in extremely hostile environments. From deep within the frozen ice caps, in the waste products of nuclear power stations, to depths of over 10,000 feet at the bottom of oceans in hydrothermal vents. These are the most primitive life forms ever found, from which we are all descended. These creatures are so tough that if a colony of these microbes were living deep at the bottom of the ocean and an asteroid struck the Earth, they would survive. Deep in the ocean, at the height of the bombardment, life carried on as usual, while up above, all hell was breaking loose. Because our early Earth had an atmosphere, this means that an asteroid strike would be a far more spectacular event than an impact on the moon. An atmosphere means gases, and gases heat up, which can create fire. Larger asteroids impacting early Earth would create fireballs as they plummeted through the air. To analyze fireballs and shooting stars, we've loaded the vertical gun, rigged ultra-high-speed cameras, and pumped the target chamber full of argon gas. We're going to fire an asteroid into the atmosphere of our early Earth.
Oh! Oh! Kapow!
Fireballs burn not because of friction, but because of ram pressure. Ram pressure occurs when an asteroid rapidly compresses the air in front of it, causing the air molecules to heat up to temperatures of more than 3,000 degrees Fahrenheit. This super hot air envelops the asteroid, causing it to glow white hot. The smoke trails are the tiny melted particles of the asteroid breaking off and burning up.
It's just like fireworks. This is kind of like every day on the early Earth would have been the 4th of July. But you just wouldn't want to be there because the entire atmosphere would have been heated by all this debris coming in.
As well as heating the atmosphere, these ancient impacts would have fractured the Earth's surface, triggering volcanic eruptions from beneath. These eruptions, in turn, would spew sulfurous gases into the air. The resulting steam would eventually cool and condense, causing rainstorms lasting more than 1,000 years. We've seen what an asteroid storm could do to our ancient world, but what would happen if we were bombarded tomorrow? Scientists know that asteroid Apophis has been on a collision course with Earth ever since its discovery in 2004. It's hurtling toward us at almost 30,000 miles per hour, and it's due to arrive on Friday the 13th, April 2029. It will pass between Earth and the Moon, below geostationary satellites, and it will be visible to the naked eye. It's going to be close, but it's expected to miss us. What goes around comes around. Astronomers now worry about 2036 and whether or not the asteroid's trajectory could reroute toward Earth.
If Apophis actually goes through what we call a keyhole in 2029, it's only 600 meters wide. And if it does go through, it will hit the Earth in 2036.
A keyhole may sound like something from a science fiction movie, but in reality, it's just an area of space directly in Apophis's path, only 18,893 miles from Earth. If Apophis passes through the keyhole in 2029, Earth will give it a tug, which could speed it up or slow it down. This could result in the asteroid entering into a resonant relationship with Earth. And in 2036, Earth and Apophis will be on another, closer collision course. However, NASA has recently calculated there's a 1 in 45,000 chance of Apophis impacting the Earth in 2036. About the same odds as being killed crossing the road. Just in case the scientists are wrong, NASA and others are developing rocket and missile technologies to deflect an oncoming asteroid. In the case of Apophis, we've got a little under 30 years to make sure the technology works. But what about another planetary storm? Could anything of that gigantic scale ever happen again? At present, the scientific community is divided.
There will be ongoing bombardments. There is no doubt about that. The debris of asteroids floating in is ongoing. It's not about to stop.
Fortunately, the impact rate has declined. We will not see the type of cataclysm that affected the Earth 3.9 to 4 billion years ago. That was a completely unique event. However, we should not take too much comfort in this fact.
Sooner or later, some of these fragments in there are going to come in and hit and raise absolutely holy hell.
Imagine what would happen if San Francisco was hit by a huge asteroid. Scientists calculate that anything bigger than 3,000 feet in diameter is beyond what they call the global catastrophe threshold. This is the point a disaster is so great that it leads to the deaths of more than 1/4 of the Earth's human population. This threshold equates to an explosive event of nearly 1 million megatons, 1 trillion tons of TNT, and over 1.5 billion deaths, 50 million times greater than Hiroshima. But we know there are 850 near-Earth objects larger than this. This is what would happen if just one of them, 3 miles in diameter, was on a collision course with Earth. It could weigh up to 5 trillion tons, depending on whether it's made of iron or rock. As it enters our atmosphere at 36,000 miles per hour, the increased air pressure does nothing to slow it down. But this pressure does heat it up to more than 3,000 degrees Fahrenheit, hot enough to melt iron and turn rock into lava. It's now about 60 miles above San Francisco. The temperature increases exponentially. The oxygen-rich air is almost 18,000 degrees Fahrenheit, nearly 3 times the surface temperature of the sun. This is the last thing you would see. Seconds later, the blast pressure pushes the ocean aside, leaving a void almost 40 miles across. The outer edges are walls of water spreading outward and upward. The ocean vaporizes. Some of the pressure waves turn to steam. Others create tsunamis, initially 3,000 feet high, that travel the Pacific at more than 400 miles per hour, destroying the Japanese coast in 10 hours. The shadow of the asteroid covers all of downtown San Francisco. It's 1 second to impact. The explosion is equivalent to almost 15 trillion tons of TNT. This is more than 1,000 times greater than the world's combined nuclear arsenal. San Francisco no longer exists. All steel and stone is vaporized. If you are within 25 miles of the impact, every cell in your body melts in an immeasurably short space of time, faster than the nervous system can register. The victims this close to the impact are the lucky ones. Within milliseconds, a crater almost 50 miles in diameter forms. This is the most powerful and devastating release of energy per unit of time on Earth. The impact generates a shock wave that spreads out across the U.S. faster than the speed of sound. Winds of over 1,000 miles per hour follow close behind, stripping trees and vegetation, killing all wildlife. 2 minutes after impact, Los Angeles is destroyed. Seismic activity is triggered in fault lines, causing earthquakes and eruptions around the globe. Less than half an hour after impact, earthquakes and clouds of black choking dust hit New York. In the seconds after the impact, billions of tons of what was once San Francisco and ocean are now in the air. This cloud of rock, dust, and steam spews outward and upward at over 1,000 miles per hour. It quickly fills the atmosphere, blotting out sunlight for months to come. In the weeks that follow, Earth enters a nuclear winter. Crops fail, entire species become extinct, the food chain is destroyed. Those of us who don't die on impact, or from the tsunamis, resulting firestorms or earthquakes, will die of cold and hunger. But that's just one science fiction view of what could happen. We can now offer a solution to what almost certainly will happen if we were ever threatened by an asteroid strike in the future. On the 4th of July 2005, NASA tested the technology that may one day save the planet from an asteroid impact. With a spaceship the size of a small car and a projectile the size of a coffee table, the Deep Impact mission successfully tracked, aimed, and fired into the center of a comet called Tempel 1. Deep Impact was a spectacular success. This technology can and will be adapted in the future to not only hit an asteroid, but to destroy or deflect it, potentially saving billions of lives. But defense against another large-scale planet storm is still beyond the reach of science.